it was funny because you would talk to somebody making 18650 cells, and they would say, just don't know how the hell LG gets that extra capacity in the cell. It's just, we pushed everything to the limit. What are they doing? Then you learn that when you look at their spec, it tells you that the diameter is something like 18.2 plus or minus 0.2, and they're always on the plus side. So people cheat. Definitely, they cheat.
But if you're a company like Tesla and you have different cell suppliers, that can be good, right? Because then your cells are not going to be identical, and that might mess things up down the road, or maybe not.
Well, I don't think they're mixing cells in a particular vehicle, right? They have all the same cells in the vehicle, in one vehicle, and then a different vehicle would use different cells.
But wouldn't you have to optimize the BMS as well for a different cell type or something, different manufacturer, some quirks and stuff in there?
Well, for example, the Model 3 that's made in the U.S. uses 2170s produced in a gigafactory, and those are all exactly the same. And the Model 3 produced in China, some of them use LFP cells coming from CATL, and they're presumably all exactly the same, right? You're not mixing and matching in the same vehicle.
Yeah, I was more thinking about if you have the same vehicle, but you have a set, certain batch of production has the gigafactory cells, another batch has CATL, then would you have to, change the electronics, also the BMS and stuff a little bit?
I don't know the details about that. I don't think it would be a big deal. All right, it's time to begin, so we will. All right, so let me try to find the PowerPoint. Okay, can you see my PowerPoint?
Yes.
Yes.
Okay, great, thanks. I've been turning down my sound because you guys are really loud. Am I loud enough for you?
Yeah, you're loud enough.
Okay, excellent. Yeah, so I wanted to talk about a simple model for SEI growth. And like I mentioned last day, this particular journal article by Lawless talks about a lot of models for oxide growth on metals. And the lithium-ion battery community has stolen one of these growth laws, which is the absolute simplest one. And it works pretty well, it seems. So the simplest model for oxide growth on metals is called the parabolic growth law. And it assumes that the rate of increase of the thickness of the passivating layer, and that the thickness of the layer we're going to call X, is inversely proportional to the thickness of the layer. So it means the thicker the layer gets, the slower it grows. So the rate of change of thickness, dx dt, is equal to some constant divided by the thickness of the layer. Okay, and for us, the passivating layer is meant to be the solid electrolyte interface. For the metals guys, it's the oxide layer. So this K is just a proportionality constant. And you can take equation 1 and rewrite it by, cross multiplying x dx equals k dt, and then you integrate this equation. Then you get 1/2 x squared equals kt plus a constant. So if you say that the thickness is 0 at 0 time, so that would be the moment you would expose a pure metal to air, or in the case of a lithium-ion cell, it would be the moment lithiated graphite was exposed to electrolyte for the first time, which should be something like the minute you start doing the formation cycle and start forming lithiated graphite, that would be your T equals 0. And if you take x equals 0 at T equals 0, then this constant C is also 0. And you can write that the thickness, you solve the equation, thickness of the SEI layer versus time goes like T to the power half. So the SEI thickness is proportional to T to the half. And if you combine equations 1 and 2, you can get that the rate of change of thickness of the passivating layer is given by dx dt equals 1/2 K times 1/2 T to the minus a half. Okay, so the SEI growth rate is proportional to time to the power 1/2. So it means that over time, the SEI growth rate becomes smaller and smaller, and the thickness gets bigger, but the rate of thickness increase slows down. So what we want to do is see how this very simple model corresponds to experiment. So this is a paper that Aaron Smith wrote long ago, 10 years ago, and it's a high precision study of SEI growth in lithium graphite cells. So these cells are cells with lithium metal on one electrode and graphite as the other electrode. So panel A shows the voltage versus specific capacity of the graphite electrode, and you should recognize these type of curves by now. So this is the first lithiation of the graphite that my mouse is tracing along. And then you recharge and you come back to the top, and there's some irreversible capacity. That corresponds to some lithium atoms that were used in the SEI. But then every subsequent charge-discharge cycle that you take, that irreversible capacity, the total irreversible capacity gets bigger and bigger and bigger. And you can see by the way these lines get closer and closer and closer that the rate of increase of irreversible capacity gets smaller and smaller. And you can also see that the shift in the delithiated state and the shift in the lithiated state are exactly the same. Okay, so what this is telling you is that there's extra lithium being delivered during the lithiation that's being incorporated in the SEI. That's why the capacity gets bigger every cycle. And that lithium that's been delivered to the SEI cannot be removed. So there's 4 cells, maybe it's 5 cells being measured here in this experiment. And panel B plots their specific capacity versus cycle count. And like I'm telling you, the capacity that's being charged and discharged is it's constant, right? You can see it's to a very high degree of precision. There is no capacity loss happening to the graphite. The graphite can still accommodate just as much lithium as it could at the beginning on every cycle, but you're losing lithium to the SEI. And then panel C plots the Coulombic efficiency. This is the discharge capacity. Excuse me. In this case, it's the lithiation capacity. No, I've got it wrong. It's, in this case, the delithiation capacity divided by the lithiation capacity. So it's the capacity measured when you remove the lithium divided by the capacity when you add the lithium again. And you can see that that's less than 1. Coulombic efficiency is less than 1, so it means the charge that you transfer to the electrode is always greater in the lithiation step than the delithiation step. And that's because lithium is being used and lost in the growth of the solid electrolyte interface. And the Coulombic efficiency gets closer and closer to 1 because the rate of thickness increase of the SEI gets smaller and smaller. Any questions about this slide? Okay. So what's very interesting to do is just plot the endpoint of the discharge, or the endpoint of the lithiation here, versus the cycle count. So that's what's being happening here with the solid symbols up above. Okay, so it starts around 368 milliamp hours per gram. And as you can see, as you cycle more and more, it approaches 400. So that's what the solid lines are doing. Okay, and this increase in capacity is all lithium that's going into the ever thickening SEI. And in this little panel, they show you how the endpoint changes every 5 cycles, not every cycle. This is cycle 1, cycle 6, and so on. And then you also do the same thing for the charge endpoint. And again, you can see how the charge endpoint moves along as the cycling increases from cycle 1 to cycle 6 to 11 and so on. Okay, and these two curves are roughly parallel, and that's because the cell capacity isn't changing. The endpoints are both shifting by the same amount in the same time, roughly. So how do you see if this fits or can be explained by the parabolic growth law? So the rate of thickness change, the rate of thickness change of the SEI should go like T to the power half. And the irreversible capacity per cycle, that's how much did the SEI thicken each cycle. So it's the rate of growth of the SEI per cycle. So that should increase proportionately to the time to the power minus a half. So what we did was we measured experiments where lithium graphite cells were charged and discharged with a 10-hour charge and a 10-hour discharge, that's C over 10, or a 24-hour charge and a 24-hour discharge, that's C over 24, at 3 different temperatures, 30 degrees, 40 degrees, and 50 degrees C. And we plotted the irreversible capacity per cycle versus T to the minus a half for these experiments. So the early cycles are shown on the right-hand side, and then as time progresses, you move to the left. And these solid lines are guides to the eye, because if this data follows the T to the minus half law, it should be a straight line. And it looks like these data are coming into sort of straight line behavior. Now you should be asking yourself, why is the irreversible capacity per cycle different for C over 24 compared to C over 10? Does anyone want to take a stab at the answer?
Because SEI's formation takes more time than lithiation.
Well, the SEI, yes, for sure, it takes longer than lithiation. It goes on forever and ever, never stops.
We can't access all the capacity at C over 10. We have to go to slower rates. And so if we go to slower rates, then you have less irreversible capacity.
Nope.
It takes longer to cycle for the slower rate.
Yeah.
Okay, so let's
I
have
think
only one person speak at a time.
Okay.
So I think I heard Aaron speaking. So Aaron, you speak first.
Yeah, I said the slower rates take more time, so there's more time for SEI growth.
Yeah, that's exactly right. Okay, so at C over 24, you're spending 48 hours for a charge discharge cycle. And during that entire time, the reaction between the lithium at the surface of the graphite and the electrolyte is occurring. Okay, so you get basically 48 divided by 20 times more irreversible capacity per cycle. So about a factor of 2.5 times more when you are going at the lower rate compared to the higher rate. It's just a question of time. The SEI is growing all the time. Growing all the time. It grows even if you're not cycling. When you're doing storage, it grows. It just grows, okay? And if you look at the data for 30, 40, and 50, you should be able to notice that at 50 degrees C, these values, at the end of the experiment are around 1. Whereas at 30 degrees C, they're less than 0.05. And that's just telling you that the SEI growth rate is greater at higher temperature, which you would expect. So anyway, the point is, if Aaron's right, and it's all about time, if we plot the irreversible capacity per unit time, these two data sets should lie right on top of each other. And so that's what we do. We plot the irreversible capacity per unit time per hour. And sure enough, the C over 24 and the C over 10 data, they lie right exactly on top of each other. So this was the first time that anybody had ever done an experiment like this. And it's a hard experiment to do unless you have an ultra high precision charger to really look carefully at this. So on the right-hand side of this graph, here we plot the total irreversible capacity. Well, the total irreversible capacity should be proportional to the SEI thickness, right? Because all that irreversible capacity is being used to make SEI. So the greater the irreversible capacity, the more thickness you should have. And if you plot that, it should be proportional to time to the power half. So if you plot total irreversible capacity versus T to the half, you should get a straight line. And you get almost a straight line. And in this case, it's like I say, it only depends on time. It doesn't depend on the C rate of cycling. So both C over 10 and C over 24 data lie along the same exact behavior. The slope of these curves can be used to extract the rate constant K. And you can see that the slope gets greater as the temperature increases because the SEI growth rate gets worse and worse as the temperature increases. Okay, so it's a good chance here to just stop and talk about this if anyone has any questions. So let's do that.
Jeff?
Yep, go ahead.
Yes, so for different additives, if you do the experiment, does the K value different for different additives?
Yes, absolutely. When you put different additives in, all of these slopes can change very much. Absolutely.
Can we say that if for certain additive, if the K value is very small, can we say like it's a better additive?
Yeah, in terms of making a very good SEI on the graphite side, yes.
Okay, thank you.
I have a question as well. So the K value changes with the temperature and the additive. Would it be possible through experimentation to find a way to calculate the K value?
Well, you'd have to do a ton of experiments. Now, here's another thing for you, okay? Imagine that you run a cell at 50 degrees C for a while, okay? So here, time is proceeding to the right. You can see my mouse moving. So say you run up to here, and the SEI has a particular thickness. And now you take that cell and you put it at 30 degrees C. So it already has quite a thick SEI, right? So when you go to 30 degrees C, its total irreversible capacity will be greater. It will be 70 like it was before. But now the growth rate will match the growth rate of 30 degrees C with an SEI of 70, equivalent to 70 milliamp hours per gram of capacity. So the slope will be way less than the corresponding cell run at 30 degrees C all the time. Okay, so why is that important? If you want to market a cell to a customer and show them that at the very beginning there's very little initial capacity fade, you'll age the cell for some period of time at elevated temperature. So for example, when I was in China, I visited a number of factories, but the BYD factory was a good example where they're making 300 amp hour LFP cells, 8 kilogram cells, single cells, big monster things. So they would make them, they would do their formation, and then they would sit at 50% state of charge at 45 degrees C for some period of time, like a week or 4 days, I don't remember. But the whole point of that was to thicken the SEI so that when the cells were given to the customer, the initial capacity fade at room temperature was basically not measurable because you've already thickened the SEI quite a lot. So history, as well as temperature and additive, all these things affect the SEI growth rate. Any more questions on this slide? Comments? Okay, let's go on. So those experiments were made in half cells, so lithium metal and graphite. So what happens to the negative electrode SEI growth in a full lithium ion cell? Well, it turns out to be basically exactly the same, but you can monitor it by looking at the capacity fade of a full cell. In the half cell, like I showed you with lithium against graphite, there is no capacity fade. The capacity is constant. The irreversible capacity just keeps getting bigger and bigger. So this paper by Leah Ellis is a study of looking at the impact of temperature and time on SEI formation in lithium-ion cells. Yeah, so I have to go to my document camera so that I can explain to you what's happening on the next slide. You'll see that she's plotting the fractional fade per cycle, and from this she's learning about the SEI growth rate. So I want to show you how this comes about. So I'll go to my camera. I think you should be able to see my document camera now. Is it true?
Yep.
Yes.
Okay. So here's the deal. You have voltage versus capacity. And the positive electrode curve might look like this. And I'm just getting a different color for the negative curve. And we'll say that this is LFP, or lithium cobalt oxide, which has very little irreversible capacity on the positive side. So during formation, the negative will look like this. And then you charge back, and there's irreversible capacity there, right? So there you are. So the cycling capacity of this cell will be from there to there, because at this point the graphite's empty, and this is as far as you're going on the positive side. So that's the cycling capacity. But what we learned in our study of the lithium graphite cell was that slowly, you know, every cycle, this curve just keeps shifting to the right. We saw it. We know it happens. So, you know, on the next cycle, it's here, and the next cycle, it's here, and the next cycle, it's over here. Keeps shifting to the right. And what that means is the cell capacity gets smaller and smaller. So if you just plot cell capacity versus cycle number, which is proportional to time, or versus time, you will see a decrease in capacity, provided there's nothing else bad happening in a cell. The only capacity loss mechanism is SEI growth on the negative side. And at elevated temperature, like 40 degrees C and above, this is by far the dominant capacity loss mechanism in lithium-ion cells that only have a graphite negative, no silicon or fancy stuff. So let's go back to the PowerPoint. Okay, so you should see the PowerPoint now. Is it true?
Yep, it's true.
Okay, so here we're plotting the fractional fade per cycle. So this is equivalent to the growth rate of the SEI. How much did the SEI grow per cycle? The amount of capacity that you lose per cycle, that lithium ends up in the SEI. So a plot of this versus time to the minus a half should be a straight line. Okay, so these experiments, measuring the fractional fade per cycle was done at 40 degrees C, all right, 40 degrees C. So this is the first cycle at 40, the second cycle at 40, and so forth. But these cells were all treated in a different way before they were cycled. So some of these cells were held at 60 degrees C at various temperatures, as indicated, and some were held at 40 degrees C at various temperatures, as indicated, right? And what you learn is, you know, it's hard for me, being colorblind, to know where the, you know, which symbol is which, but I can tell that these are all sort of greenish or brownish or something like that, or maybe red, whereas these ones are more like blue and purple. That's the limit of my ability to distinguish them. And I can tell that all the cells that start at 60 degrees C start with a lower fractional fade per cycle. Why is that? Because during that 60-degree time, they developed a thick SEI. Okay, and the ones that started at 40, whatever happened to them, they developed a thinner SEI at 40. But then over time, you know, and this is many, many hundreds of hours to get over here, everything ends up reaching the same point, because the SEI growth at 40 degrees C, where all this testing is done, you know, they eventually all come to basically the same point. You know, so, and there you can extrapolate these back to zero, because you're following this t to the minus half law. And it looks like, you know, no matter where you start, you're always going to end up with a cell that's going to die at the exact same rate. So the reason to do this type of thing at the beginning is so that the customer in the early cycles sees a very small capacity fade rate, but it doesn't affect the long-term cycle life of the cell. Now, people, if any, on the call that work for Tesla will know that complicated formation procedures are used in manufacturing. And it's always a question, you know, when you do an experiment like this and you learn after several hundred hours, it really doesn't matter what you did after the formation step, you still get the same result. Okay, so any questions about this? Hopefully I was clear. You know, and you could ask the question in our lab, why do we do all our formations at 40 degrees C the way we do it? I mean, we do it for consistency, but we could certainly change. And sometimes when we have an imminent power failure, I tell people to just do the formation at C over 10, not C over 20. It doesn't matter. You know, in the end, you're going to get the same thing. Okay, so if you have a situation where you only have capacity loss due to the thickening of the negative electrode SEI, then the capacity of the cell should be the initial capacity times 1 minus a constant times t to the power half. Okay, so these data here are described in this paper by Riza Fathi, and it's from 2014. So these are lithium cobalt oxide graphite cells. They're only going to 4.075 volts. And at this low voltage, positive side reactions with the electrolyte are very minimal. It's at 37 degrees C. There's cells that have been running for, you can see, 11 years here. 11 years. That's a long time. And these green curves are what you would predict for this capacity loss with this very simple model. And it's decent. That's the point of this. It's a decent fit to these curves. Now it's very, very likely that, you know, the SEI growth is not governed by the t to the 1/2 law exactly. And how it is exactly, you know, what exactly its growth rate is, you would need to have some very high level understanding of the film, which doesn't exist. So this works pretty well. And I like it because it's simple to understand, you know, how changes to temperature affect A. Increase temperature, you increase A. So I think this is a pretty good way to describe capacity loss when the only thing going on is loss due to the SEI growth. Okay, any questions about this? Okay, hearing none, I'll go on. Okay, so that's all I want to talk about with respect to the SEI. And now I want to start talking about electrolytes. And electrolytes are pretty fascinating. And, you know, in our group, not too many people that work on physical properties of electrolyte. Eric Logan did a fantastic job beyond belief. He's probably listening and getting a swelled head, but really incredible job understanding electrolyte physical properties in his master's thesis. It's just beautiful. So the first thing that you want to do is measure electrolyte conductivity. So this is a very simple measurement. If you just imagine two flat plates of metal that are separated by a small spacing, 1 millimeter or 2 millimeters or something, and you just dip them into the electrolyte, and you measure, you apply an AC voltage and measure the resulting AC current. That's proportional to the conductivity. So, you know, these are what conductivity cells look like, and they would have the two metal plates, maybe you can see them here, dipped into the electrolyte. You apply the AC voltage, you measure the AC current. You know that's proportional to the conductivity, but you don't know what the proportionality constant is. So you put a solution of known conductivity into the beaker that you're dipping this into, and you can determine this proportionality constant that's the cell constant in such a simple way. So it's really simple. People may not know what blocking electrodes are. A blocking electrode means that an ion comes to the surface of the electrode and cannot be incorporated within the electrode. So a counterexample is graphite with lithium ions coming nearby, because the lithium can intercalate into the graphite. A blocking electrode for lithium, a good example would be stainless steel. The lithium can't go into the stainless steel. Okay, so a conductivity cell is very simple. Now we have them. If anyone's interested in measuring electrolyte conductivity, you can do it. And this is a typical graph of electrolyte conductivity as a function of lithium PF6 concentration at 4 different Kelvin temperatures. So as temperature increases from 263 to 333, conductivity goes up. And there's this very strange shape, right, where the conductivity increases almost linearly at low salt content. And that's what you expect, because the number of carriers, the number of ions in solution, increases with concentration. But then the conductivity does not continue increasing anymore with concentration, and it rolls over. So long ago, people became interested in trying to understand, what the shape of these curves is all about. And I'll discuss that now. So why does the conductivity versus concentration curve have such a shape? Conductivity increases linearly with concentration at low concentration because you have more carriers, more ions in solution. It's as simple as that. And then people say that as the concentration increases, you get what's known as ion pairing. So that means there's less carriers with concentration, so the conductivity drops. I want to spend a moment on my document camera just talking about ion pairing, okay? Just so it's clear to everybody what's going on. Where are we here? My God. Okay, you should be able to see my document camera again. Is it true?
Yes.
Okay, so if you have a low concentration solution that's dissociated well, you have a lithium plus that's in a solvation shell. So these little ellipses are meant to represent a solvent molecule. And then there'll be solvent molecules around. And then over here, there'll be a PF6 minus also in its solvation shell, whatever it looks like, okay? So this thing, as it moves through solution, the ion and its associated solvent shell, it has a net charge of +1, so it's a charge carrier, right? But if you increase the concentration a ton, and you get situations like this, that's a positive charge, and that's a negative charge. Well, they attract each other. And the reason that they're far apart is because they can reduce their energy by dissociating and being isolated like this. And the energy the reduction in energy is quite dramatic. I don't know if any of you have ever tried to mix a large volume of electrolyte solution. If you try to mix, 100 mils even, and you put the LiPF6 in the electrolyte, in the solvents, that solution's going to get hot because this heat of solvation is big, right? Okay, but when the concentration gets large, you'll end up with situations that are approximately, you've got the two ions in a sort of a joint solvation shell, And that thing has 0 net charge. So once the concentration gets big enough and you start having these ion pairs don't contribute to the conductivity. There's no net charge here. As this moves, it's not carrying charge in the solution anymore. So that's what ion pairing, the impact of ion pairing. Now, where was I? Here. Okay, you should be able to see my PowerPoint again. Is it true?
Yep.
I guess it's not full screen yet. Here we go. And then finally, another reason why the conductivity decreases at high concentration is the viscosity of the solution increases with concentration. And the conductivity is approximately dependent on 1 over the viscosity at fixed temperature. So the conductivity drops once the viscosity becomes very large. So this is very simple to understand qualitatively. If you take the ion in its solvation shell and you think of it like a little ball, and this ball is trying to move through the solution, and the solution is very viscous, this ball will not have an easy time moving around. Whereas if the solution is not viscous, the ball will move easily. So classically speaking, the impact of viscosity is easy to understand. Now what Eric showed, which I think surprised a lot of people in the lithium battery field, is that this ion pairing is not a very big deal, even up to 4 molar concentration in typical electrolytes that we work on. So we'll see later on that this is not often seen in the electrolytes that we see, and all of the conductivity drop with concentration comes about from viscosity increase. Okay. So to give you an example of what people were thinking in 2001, and this, by the way, is a paper by Kong Xu and Richard Zhao. Okay, so these 2 guys, and also Shenshui Zhang, these 3 guys at the Army Research Lab, these are like God 1, 2, and 3 of electrolytes. All right, these guys know what they're talking about. But this was a nice paper because it showed a lot of experimental data, and then it talked about the reasons for the things, why they changed the way they did. So they measured, this is a lot of work, by the way. Eric Logan can tell you this is a lot of work. You have to mix up all these solutions. This is ECEMC 3 to 7 with different concentrations of LiPF6. And then you have to measure conductivity at all these temperatures. And then you plot this graph. And then you mix up a whole bunch of other electrolyte solutions with ECEMC 5 to 5, 4 to 6, and 2 to 8. And what I wanted to show you in this chart is a couple of things. First of all, the conductivity increases with temperature. That's obvious. But next, if you look at the maximum in the conductivity as a function of molality, the concentration at which the maximum conductivity occurs shifts with temperature. So you might say, oh, I want to make the highest conductivity solution of ECEMC 5 to 5, and you're operating your cell at 20 degrees C, so you pick 0.9 molal. But then you realize when you discharge cells or charge cells fast, they have internal heating, and their temperature would be more like 50, and you say, I should have made a different concentration electrolyte. So it's just good to know that electrolytes behave like this. And then in their paper, they talk about the reasons for these changes in these curves. So let's see what they have to say. Okay, so they say the behavior of the conductivity of the current electrolyte system with changes in molality, EC to EMC ratio, and temperature can be satisfactorily explained by the following three factors and their dependency on molality, fraction of EMC, and temperature. The first is the number factor, the number of dissolved ions per unit volume of the electrolyte solution, right? Since these ions respond freely to the applied electric fields, the higher the number is, other variables being equal, the higher will be the conductivity of the electrolyte. So that's the linear range at the low concentration region. This number is not always proportional to the salt content M, and then they talk about because of ion pairing. You know, even though the concentration is larger, if you have a bunch of ion pairs, they don't contribute to the conductivity. And we'll see soon that this is not very true for our electrolyte systems. The second factor is the dielectric constant of the solvent. A solvent of high dielectric constant shields the ions of one charge from the attraction of those of the opposite charge, thus preventing this ion pairing of the electrolyte. Okay, so higher dielectric constant can help prevent this ion pairing that is not a good thing. And then they say the third major factor determining the conductivity of the electrolyte is the viscosity, right? Other conditions being equal, an electrolyte of lower viscosity will have a higher conductivity as the charge carriers move more easily in such an electrolyte in response to an applied field. Okay, and this is fully true. All right, so this says 2 years ago, but it should now say 4 years ago. You know, we believe this picture of electrolytes, but now we've learned that ion pairing really doesn't happen very much in these EC-based electrolytes. And viscosity is the most important thing in reducing conductivity at high molarity. So I'll spend a few minutes showing you where that comes from. I guess that'll be next day. But for now, we're going to talk about why do we care about, you know, electrolyte conductivity? Well, when you're trying to charge lithium-ion cells at high rate, and you use electrolytes with EC and DMC, lithium-ion cells can perform poorly at high charge rate. So here's an example where you have a 1C charge, maintaining capacity fairly well, a 1.5C charge, one cell starting to die, and when you try to charge in 30 minutes, both of these cells are failing pretty badly. And this is because the charge rate has been made so high that the overvoltage developed in the electrolyte is so large that the graphite electrode is pushed below 0 volts and you get lithium plating on its surface. So the transport properties of this electrolyte need to be improved to accommodate a 2C charge. Any questions about that?
Jeff, can you give a simple explanation on the what is overvoltage? I've heard of this concept. You mentioned it multiple times, but I haven't heard you talking about this definition.
Yeah, what it is the difference between the position of the voltage composition curve when measured at incredibly low rate. So if you measure the voltage composition curve at incredibly low rate, I think that's a good time for the document camera here. So I'll put that on. So let's talk about graphite. So we're going to plot the voltage capacity curve on a very blown up scale. So this might be 0.25 volts versus lithium metal. And this is 0. This is what you would measure if you measured incredibly slowly, both adding lithium and taking it out. So this might be C over 2000 rate. And actually, we have data in our lab for lithium insertion and removal in graphite measured at a C over 2000 rate that Chris Burns measured. Could I find it? I doubt it. I don't know where it is. But anyway. Okay, so then you start running at higher rate. And what you'll find out is this curve is shifted down. And in our laboratory, we call this delta V. This is half of delta V because we're only talking about the discharge direction. Okay, and that shift down, that's called the overvoltage. And it comes about from several factors: solid state diffusion in the graphite particles and the concentration change in the electrolyte from one part of the electrolyte to the other. We're going to come to both of these factors in this set of notes. But the issue is, if this lithiation rate becomes too large, this shifts down even more, and part of the curve goes below 0. And when that happens, the lithium would rather electroplate on the surface at 0 volts. Okay, so the portion of the overvoltage due to the electrolyte is what you want to minimize. And you can do that by improving the conductivity of the electrolyte and the lithium diffusion constant in the electrolyte. And we're going to talk about all those things in the next few lectures. So hopefully that answered your question a little bit about what is overvoltage.
Yes, thank you, Jeff.
It's a term a lot like oxidation and reduction, okay? It's a term that makes you sound like you know what you're talking about. You know, somebody might say, oh, well, this electrolyte additive is being reduced on the graphite electrode. Well, can you tell me the reaction? Can you tell me the products? No. But it makes you sound like you know what you're talking about. And here you talk about overvoltage, and you know it comes from several sources, and you don't know in detail which one is dominant, but you can mess around with the electrolyte and learn that you can make the overvoltages less. Okay. All right, I see we've come to the end of time. So we'll stop here, and we'll come back again Wednesday, since Monday is a holiday. Any final questions before we stop? Okay.